Hello everyone, hope everyone is doing well. Welcome to the third lecture of Applied IoT. Right. Before going into the topic that the topic in hand, characteristics of IoT, we in the last lecture we came up to sensing and perception, right? And before that we went through some initial subject matter, right? Let's try to go through them again and have uh, refreshment of to our minds what has taken place. So first we looked at the introduction of IoT. We looked at IoT devices, examples of IoT applications. Then we took an introduction to applied IoT, and right now we are talking about characteristics of IoT. Or another one would be characteristics of applied IoT. Right. We talked about the introduction of IoT. Internet of Things describes the network of physical objects or things that are embedded sensors, actuators, processing abilities, software, and other technologies for a purpose of connecting and exchanging data with other devices over the internet. We talked about examples, as you can see: cameras, thermostats, lights, motion sensors, so on and so forth, right? We talk about some control units as well. Control sensors, it could be a small touch panel in your home, Alexa, it could be a control center, it could be your smartphone, it could be anything. We talked about industrial used IoT devices like the robotic arm, in medical industry, smart hospital beds, gaming industry, virtual reality. Smart homes include smart fridge, Roomba vacuums, and of course in any industry, any level, you can use any domain, you can use smart locks. Then again, health monitoring, autonomous driving, weather monitoring. We talked about all those devices which are there. Then we talked about application of those IoT devices. We looked at a single application from one IoT device to communicating through the internet to another IoT device to control temperature, right? Then we looked at a scenario where we looked at a single scenario and how IoT devices work together to control that single scenario, in this case which was fire controlling. Then we looked at a single set of IoT devices being used in different domains, industries, and different scenarios. In this case, it was monitoring of weather in real time and how that can be used to control all lighting in smart homes, smart cities, and how the data can be used in different industries to make decisions correctly in real time, right? Then we looked at an example where a set of IoT devices mix and match between set of industries and domains. After understanding IoT and its applications, we looked at introduction to applied IoT. Applied IoT refers to the practical application of Internet of Things technologies and solutions in real world scenarios across various industries and domains, right? So applied IoT is what we are learning here is the practical application of IoT. It is not a IoT single device or embedded system, but IoT itself. How can we apply IoT itself to different industries and domains? It involves using IoT devices, connectivity, data analytics, and cloud platforms to solve specific challenges, improve processes, enhance decision making, and create value. Why we use applied IoT? Why we learn about applied IoT? To solve specific challenges or problems, to solve problems, improve processes, right? Improve processes which are already there. We talked about the fire containment scenario, enhance decision making, and create value, right? And we went back to our examples. We learned about how we can apply it there. Then we went through a couple of examples from customer electronics to smart infrastructure, security, transportation, healthcare, industries, retail, power grids, agriculture, logistics. We talked about many scenarios. Now we took an introduction to how these things are being applied, right? And how IoT devices can improve processes and help decision making by collecting necessary data, right? So now characteristics of IoT. We are on characteristics of IoT in a sense, right? In a sense that these characteristics are characteristics that will be there when you apply a IoT system to resolve some problem, right? That is the main part that you should understand. When I say characteristics, we took an introduction to applied IoT, and when that IoT is applied either to solve specific challenges, improve processing, enhance decision making, or create value, right? When that IoT is applied, when that IoT technologies, solutions, or IoT systems are applied to a specific domain or industry, these are the characteristics that could be seen in such a IoT scenario, right? This is not something that is set on stone, right? This is not something that is universal, or it's not but these are the properties or the characteristics you will see in an IoT application or a IoT system. So first things first, we talked about connectivity. We talked about IoT devices, and the main characteristics of IoT is connectivity. There is connectivity to a network, a intranet, or the internet, right? So what is being networked? The main portion of IoT is Internet of Things. So we found the internet part. That means it comes through connectivity. Of what are the things? Things are the perception or sensing, right? The perception layer, the sensing layer, or the hardware layer of IoT. It basically the things, the hardware things that we talked about as IoT examples, which has either sensors, embedded processing, or have actuators to function, right? When sensing and perception layer comes into that, we are talking about them, right? We talked about how the sensors can check their environment and understand their environment, right, using different kind of sensors. Because this is applied IoT, we will not be going into specifics of sensors or how those are programmed and so on and so forth. But from the examples we talked above, you will now understand that there's a connectivity layer, and there will be a sensing, that means a physical hardware layer, where it would use different sensors or actuators, or mainly sensors and actuators, to either take in information of the environment or do some kind of action, right? If you talk about connectivity, and if you go to either a Roomba or let's say a robotic arm, we talked about the examples. We talked about a sensor, proximity sensors in a Roomba, and the actuators which are working together, right? it to move around, vacuum material in, and so on and so forth. And to do that, the sensors and the actuators, the motors that are driving the Roomba should be networked. So it's a small embedded IoT device, and of course this Roomba will be connected to the internet, because you will be able to control the entire thing through an app, right? Robot arms, again, rather than using this example picture, I will go right here, right? This is, we are talking in the future, but here is a good example. These robots are these robo arms are working together, right? They're working together to let me enhance this picture a little bit, right? And right, these robot arms are working together, right? But how are they working together? Which arm, how do they know how to do what at which particular position? One is cutting, one is welding, one is gluing things together, one is using rivets, one right? So that means there will be proximity sensors, there will be gyroscopes, there will be different kind of sensors. A full-on data center or a cloud environment to process the influx of data, which arm is at which position doing what at any given time, right? And those data will be then processed to see which arm needs to do the next action, which arm needs to stop the action, and those data will be fed in real time. So real-time processing of data is taking place, right? The arm itself is working entirely out of actuators, right? So here you can see the arms are networked together. They are networked between each other, they are networked internally between their sensors, they are networked to the internet and cloud processing, or if it is inbuilt data center with sufficient processing power and data handling capabilities, it would be an intranet, so on and so forth, right? So we see the networking aspect of it, we see the sensors, actuators, right? We see the perception layer of it, because it's a physical hardware layer. So when coming into IoT, these are the main two things, right? But so we talked up to that particular point. Then we come into data analytics. Why data analytics is there? First, let's read through data analytics and try to understand what we are trying to mean by data analytics. IoT generates a massive amount of data from various sources. Data analytic techniques and algorithms are employed to process and extract meaningful insights from this data. This enables data-driven decision making, predictive analytics, and optimization of processors and systems, right? So when we talk about this topic, when we talk about data analytics, I think the first thing that you should come to our mind are the examples that we were giving, right? We are in a way talking about big data. We are talking about a large number of sensors producing large number of data, right? And that data have to be stored somewhere, and that data have to be processed. So basically what we are talking about, big data, or another way to put it is cloud computing. If cloud computing is needed, right? If cloud computing is needed, that means those IoT devices have to be connected to the internet. It won't be just connected to a intranet, right? We talked about connectivity, we talked about sensors. Now data analytics. So IoT generate massive amounts of data from various sources. Let's go for example above and try to understand, right? This one. So we have weather data. We collect them. We collect the weather data. We use them for different scenarios. We talked about them, and we talked about weather monitoring devices, those IoT devices for this application as well. So weather monitoring devices, are they producing a lot of data? If they are producing data in real time, every second or every 5 seconds, right, whatever the way that the program is written, wind speed will be uploaded into the internet, temperature will be at that location will be updated, humidity will be updated, temperature will be updated, either if it is raining, likewise, if it is snowing, likewise, the amount of rain we got, the amount of snow we got, so on and so on. So when monitoring weather, multiple number of data, multiple sets of data will be constantly updated to the cloud in real time, and not only one location, right? You can't have a weather monitoring device in one location for an entire country or an entire region. There will be multiple. There will be in a larger country, right? Even if you are in Sri Lanka, right, a small distance is enough to change the weather from becoming cold like if you're going from here to let's say Colombo to or Kalania to Nuwara, how much the weather changes. Now apply that to a country like India, China, United States, Canada, and the differences are humongous. And if those countries needed to keep an eye on their weather in real time at all times, we are talking about thousands and thousands of weather monitoring devices located all around the country, feeding data into the cloud. That means large amount of data is being fed into the cloud, and that particular data should be processed in real time. Now we go into how the application part happens. Application of IoT takes place, right? We need, so these so it says a massive amount of data from various sources, right? In this case we are only taking weather monitoring IoT devices, right? Even in that, it's not one set, there are couple of topics to be covered again: wind, temperature, humidity, so on and so forth. Okay, so those, let's say 1,000 weather monitoring locations will be feeding data into the cloud, right? Data analytic techniques and algorithms are employed to process and extract meaningful insights from this data. If you have seen weather channels or weather forecasting systems, what they actually do is they have a large database of data collected throughout the years. They compare that data through algorithms between the humidity right now. If the humidity is this much, if the sunlight is this much, if the wind speed is this much, can it rain? Or this is a simple example. I'm not giving I'm not trying to give a complex every data point, but I'm just saying, okay, if this scenarios are like this, will it rain? That is basically a small example of analyzing the weather. So that's a decision making ability, right? So here it says to extract meaningful insights from this data. So number one, if real-time data is given around the country from thousands of monitoring devices, at all times people from different industries would have real-time data of the weather, and we talked about how it could be applied, right? Controlling the temperature, right? That is one of it. We can apply it for controlling the temperature. People who are going in remote areas, people who are going in fishing, aviation, those industries can get real-time values of the weather. And smart cities, lighting systems for roads can get real-time weather information, the intensity of the light, to make the decisions, to make that particular decision, right? We talked about the efficiency and everything, so that you can see that that is a decision making application. And again, if you take a power grid, real-time data, now you see how things, when Internet of Things comes alive, how different sectors are talking to each other. Now weather monitoring devices are talking to the power grid. How are they doing that? When real-time data is given, or if that data is used to predict the data in the future. If it is a cloudy day, the nights are going to be a little bit colder than usually sunny days. Things like that. To predict things like that, right? When those things are predicted, right? Let's say it's a country with with winter, and that day the sun was not out. It was very cloudy, right? There's no sun, maybe for 1 or 2 days, which means at night the temperatures are going to go very low. That means people are going to switch on their heaters a little bit more, right? And if it is IoT system, it is being done automatically, right? Then when heaters started working a little bit in a higher temperature, more energy is consumed. If there are 1 million people living in that city, that means even a little bit of a change will need a large output of electricity. So the electricity grid could be ready. The electricity production, the amount of raw materials needed to produce the electricity, the energy needed to be supplied, the electricity grid could be ready in respect to the data which is collected by the IoT weather monitoring devices. Now you can see how the data is being applied throughout different industries and domain, right? Next to the power grid is the agriculture, and when coming into weather and agriculture, there is no need for explaining why it is so important, right? So if you go back again to this definition, right? Extracting meaningful insights from data, right? So that means we can get real-time data, plus we can use that real-time data, compare it with old data, and predict the future weather as well. So this is decision making. This enables data-driven decision making. That is what I'm trying to say, right? So if you take applied IoT definition, right, it says enhanced decision making. Will it enhance decision making? Yes. It will not only enhance decision making, it will also automate decision making. But in this case, if you take the single example, this is just a single example. We are talking about only monitoring weather for our convenience, and you can see how it affects the decision making of each and every domain and sector. When coming into power grids to agriculture, how it is being done, right? Let's say the weather, okay, the wind is this much, is it cloudy or not, is the humidity high or low, and the prediction is in the next 24 hours it's going to rain. Then farmers doesn't need to water the plants. There will be enough rain to water the plants. Say that means in some countries farmers have to pay separately for the water. In Sri Lanka, no, actually the water is taken care of by the government itself. We have tanks that are being built not only from the current governments, but hundreds and thousands of years ago, or the rulers from that time onwards has supplied water to the agricultural sector. But that water could be saved when it's mostly needed, when there are droughts, when there are situations like that. We can save that water and use the rainwater, which is from the predictions, from the data models of weather predictions. How we are doing that? We can do it by IoT, right? So data driven decision making, predictive analytics, we talked about it, right? We talked predicting, looking at the data now. We are looking at the how it's going to be in the future. Optimization of processes and systems, right? Again, optimization. If so, the decisions are in the power grid, the decisions are making to optimize it if more power is needed or less power is needed, right? By looking at the weather conditions. These days, the month of April, very hot and very humid in Sri Lanka. The amount of the amount of ACs or the fans or cooling units that are being used in daytime becomes high, right? So obviously the electricity consumption is going to be high. Coal power plants, if they want to stockpile their material, right, coal to burn, and or gas power plants, if they want to stock their material, right, they should know from the data which is being collected through IoT devices, especially monitoring the weather. They should be able to make these predictions and be ready to give 24 hours of electricity without any unbalance in consumption, right? Not and if they know that it's a day where less material is going to be used, they don't need to waste their product, coal or gas. So if you take hydroelectricity, don't need to waste the water as well, right, depending on the temperature. Of course, again, we took the example for this one as weather and temperature, right? The taking Sri Lanka as an example, Sri Lanka is a small country, so small area to monitor. But if you take larger countries like India managing, let's say in agriculture, managing water, there are countries like if you take United States or Canada, right, where there is large differences in temperature, and we are talking about large huge countries in landmass, right? IoT devices are a key in predicting and decision making, right? So now you can see how the large amount of data which is being produced by all these IoT devices, right? We talked about only one, but there one set of IoT devices, but all those data can be accessed through the internet when it is fed to the internet, and the amount that is generated is massive, right? IoT generates a massive amount of data in various sources, right? That is when data analytics comes into play. Now you understand how that massive amount of data can be used in different domains and different industries for, again, decision making, optimizing processes of systems. And in applied IoT, that is what we are concentrating on, how to apply IoT to improve process, enhance decision making. So that's how data analytics works in this. So now we know that upon characteristics when considering IoT system, that IoT would create a large number of data, right? Especially when that data is needed in real time, right? Think we have taken weather as an example, right? And we have gone through how it can apply. Think of a security camera system. If there is there's needed to be image processing, and if image recognition software have to be used, you can see the amount of data. If a HD video is being produced, the amount of data that is needed to be uploaded into the cloud, and the amount of processing that would need to back that situation up. So depending on the scenario, anyway, a IoT system would include multiple number of IoT devices, and these devices would be producing a vast amount of data. The next feature that we will see, or the next characteristic that we would see in a IoT application, would be automation, right? Automation and control. We talked about how machines with IoT devices with sensors taking in data, and that data being processed, and that processed data, the outcome of that processed data is used to give commands to other IoT devices to take action, right? IoT enables automation and remote control of devices, systems, and processors. Through IoT, devices can be motioned, controlled, and managed remotely, allowing for increased efficiency, reduced human intervention or human error, and improved responsiveness. So if you go through that again, right? So the ability is given that we can control everything remotely from maybe from when saying remotely, it would be from a distance, not at the machine itself, right? It what does automation and control gives? It gives increasement of efficiency, reduced in human intervention, and improves responsiveness. These features, when we were talking about examples of fire control, if you remember how the smoke detectors detect the smoke, then automatically it will be like after the network will carry the data through to different places, and that would be the places would be a control center. The control center will then automatically can control the sprinkler system or a fire suppression system. Then that data could be fed into people who are in the building, owners of the building, to act accordingly, and the fire station to act. So this means if you take the first part of it, from detecting a fire and using the control system to activate the fire suppression system, right, activate the water sprinklers, that part could be done without any human intervention. If the code is written, if the commands are there in the code, in the parameters are given in the code, right, that can be done. So that means such a automated process will increase efficiency, improved responsiveness. We highlighted this because if it is late at night around 3 a.m. in the morning, there will be less people to react. But if it is automated, instant reaction will be there, and that will of course help to save lives, help to save property, right, so on and so forth. That means that this automation of use of IoT for automation is a very important part, and it is a value adding activity, right? And reduce human intervention. Again, there could be human error, right, in judging such a scenario. Plus reducing human intervention means like at late at night, if a fire occurs, a human doesn't need to see the control panel or doesn't need to see the fire itself to make that judgment. The judgment will be made automatically through the IoT system, right? If the heat, comparing the heat levels, comparing the smoke levels, the system, the IoT devices will relay that data to a processing system. The processing system, it could be a control system inside, or it could be the cloud itself, right? They will check the data under the parameters, right, with the code they have, and if the parameters are met, the sprinkler system can switch on, right? So that is a good example for automation. And again, when coming into automation, we talked about production line automation, right? We have a person remotely controlling in mining, automation of logistics, automation of other industries. We talked about it. We talked about how automated tracking of logistics takes place, and so on and so forth. So a big part of automation is IoT, right? From GPS tracking devices in logistics to, right, so again, a large number of data would be processed, right? If you have a company which you drive, let's say taxis, and you have 100 taxis, or if you drive buses, you have 100 buses with you, and those we can have a real-time reading of where the buses are at any given time. And of course, automation and control, big thing when talking about vehicles is autonomous driving vehicles, self-driven vehicles, which is little by little becoming the future. And every self-driven vehicle is a IoT, part of the internet. They will share data with other. If you go through Tesla systems and how they share data, how they process data, you will understand how Internet of Things, how the Tesla car becomes an Internet of Thing, right? Thing in the Internet of Things. Then from data analytics, automation and control to stability, right? So now stability, what does this mean? This is also a feature that has been seen in IoT. IoT systems can scale from a small number of devices to millions of, even billions of devices, and infrastructure and platforms supporting IoT must be able to handle throwing number of connected devices, data streams, and interaction. So the stability part of it is the data we use, the networking systems we used, if it is either the cloud resources we use, or the data center resources, or the processing power we use, right? If you are making a IoT system, there is the potential for scalability, right? Let's say if you have a factory, let's go to this example again, right? Like to get a visual representation. Now this is one line, right? Let's say this manufacturing line produces a car every 5 minutes or 10 minutes. If they want to increase the production, that means they have to replicate this line totally in another place, right? So every sensor, every actuator, every robotic arm, every software, everything, it should be replicated, right? If you have this logistic unit, right, if you are going to use these IoT devices, if you can see that these are self-driven IoT devices to deliver the packages to the right slots in this logistic place. Let's say in the month of December, there are more gifts going on, there are more packages going on. So That means the amount of devices that is needed to be used, the amount of IoT devices that is needed to be used have to be increased, because the number of packages increases. Then to handle that packages, the number of IoT devices have to be increased as well. That means the system itself, the network should be the network should be able to scale up, because if more devices are working, that means the more there is a lot of data created, and that data would be sent to the cloud by networking. So the network should increase with it. The amount of sensors that are working should be increased with the amount of actuators that are working with it increased. So that means IoT have this unique feature to keep adding devices, right? So if you say here in the definition, these IoT systems can scale from a small number of devices to millions or billions, right? If you take an electricity grid, and if you are to monitor every small position of these, if you want to check the weather, if you want to check the heat of the cabling, if you want to see how much electricity is being transmitted, is the system balanced and everything. So each IoT monitoring device is right there. There will be from the plant to the closest distribution center or to the city itself, there will be at least 1,000 monitoring IoT small devices monitoring the electricity. If that grid needs to expand, right, we don't need to add a new control center, but that control center itself should be able to expand and handle another 1,000 IoT devices to monitor the new electricity distribution line. Right? So this is what it meant by scalability. If you have a home and you build a new partition to your home, a new area of your home, you will be able to use the smart home system that is being used already in that home, extend with more IoT devices into the new section or the new annex of the home which was built. If you have a security system, you will be able to add more motion detectors or more security cameras. So it is the scalability of it. IoT does not have limitations when coming into scalability, right? When you give a IoT solution to, let's say we are using a metro system or train system, IoT devices can be used to give surveillance, to see if all doors of the metro system is closed, when the doors are closed automatically, if the motors are working fine, which train is at which point, so to avoid collision. So then again there will be sensors to detect any collision detection and so on and so forth. And if that city decided to add a new metro line into it, or the railway department decided to add 5 new trains to their existing system, the IoT devices of that train, right, should be able to integrate to the current system without any problem. That is a feature of IoT. The scalability, right, it works the other way around as well. If you remove 5 trains, it should be also able to handle without a problem. So basically the scalability is there without needing to add anything new, right? We only have to check whether, okay, what the amount of data that is needed and the processing power and those things. But if these things are needed to be added to a system, right, the scalability would be there. So that is also a main characteristic of IoT. When applying IoT solution, if you are to apply IoT solution to any place, any location, any so example, let's take Tesla cars for example. So we were talking about devices. We said that we can consider the Tesla car itself as a IoT device. So think about every day, every month, there are hundreds and hundreds of cars being added to the system. There are hundreds of new self-driving cars with different features added to the system, and that data is fed into the internet, right? And the car itself is an embedded IoT system. There are many sensors working together to give to help the car drive by itself, right? But then again, all that data is fed into the internet as well to process, and if any new information is seen, that will be updated to rest of the cars, telling okay, at this situation, at this location, you can take the turn or accelerate or deaccelerate to have a better driving ability. So that means that particular IoT system, the scalability is happening as we speak, right? So these are examples. So then again, we talked about connectivity, sensing and perception. These things, that means the network and hardware, those 2 points are the pillar stones of IoT. Any IoT, even a single IoT device, right, working by itself, should have connectivity and the perception layer. Then we talked about other features or characteristics which would be there on IoT devices. If there's a lot of IoT by nature creates a large amount of data, right? We should be able to process that data, analyze that data for, again, we talked about enhanced decision making, improve processes, right, for those things. So the large amount of data is necessary. Automation and control systems, again, we improve processes, right? We talked about how without human intervention automatically these processes can proceed, right? Enhanced decision making, we can enhance it by making quick decisions through automation, right? The decision is already made, we will type it onto the code, and when the parameters are met, that decision would take place, the commands will go out, right? So things like that, we talked about it, right? Then again, the scalability of it. So we talked, that is also important thing when some kind of a IoT system is applied in an industrial scale, right? So that the companies must can be reassured that if they are to expand, they can expand using the current IoT system. So those are 5 characteristics. Let's look at the sixth characteristics. The sixth characteristic of IoT when IoT system is applied. Security and privacy. IoT presents unique security and privacy challenges due to the vast number of interconnected devices and the sensitive nature of the data they handle. So we talked about the vast number of devices, right? Now we are talking about the security aspect of it. Strong security measures including authentication, encryption, access control and data protection are crucial to safeguard IoT systems and preserve user privacy. So when you are designing an IoT system or IoT platform, if you are using those devices to automate things, right? If you are taking a factory line, right? If you are going to automate the process of pumping, if you are going to automate the process of this factory line, you must make sure that nobody will be able to hack into that system, and disrupt it. You must be able, so these are company secrets, how many vehicles are being manufactured, and those things could be count from the data which is produced from these IoT devices. Those must be safeguarded. If you take this pumping station, let's say extreme scenario, this would be a pumping station to pump water to cool down nuclear power plants. And if the system is automated, so there will be IoT device to detect the temperature, and according to the temperature the pumping will take place of water to cool down the nuclear reactor. So it is in such a scenario that the data which is being obtained about the temperature should be, and the amount of water that is being pumped in should be classified, and no changes could be made by external forces, basically hacking and all the security things. So why does this security and privacy comes into play? Because IoT can be applied into highly sensitive situations, and if we are, according to the definition, right, going to enhance decision making. If you are going to enhance decision making, first the data which is coming from the sensors should be accurate. The storage of that data, then we will go to cloud computing itself. If you have learned about it, there are several measures for security to store. If you are going to store data, if you're going to process data, to whom the data can be accessed, and so on and so on. Plus, on top of that layer, there is the network layer would also need security, because if anybody has learned networking, security is network firewalls are one of the main components. So we have already discussed there's going to be a large massive amount of data which is going to be produced by another massive amount of devices. So why do we have to have the characteristics of security and privacy on this? Is because of the large amount of devices that are being involved in that network. If one device is compromised, maybe that compromisation of that device could lead to compromisation of other devices. So one or two devices being hacked, the data which produced will be completely incorrect, right? If you have seen spy thrillers, right, movies, you will see that hacking into security camera systems and so on and so forth. That means if the security camera system is on in a IoT is IoT, and it's in IoT system or IoT network, then you can see that there will be devastating effects, right? It will destroy the value. It will destroy the processes that it is doing, especially the automation parts and those things. Decision making cannot happen. The security guards won't see, will not have visibility, so on and so forth. Not only that, again a large number of data and those things will be there. So if you take companies that are involved in mining and large scale multinational companies, their security and their data is really important, because the world is keeping an eye on how much of resources are being produced. It could be the security concerns would be coming from other competitive companies in the industry, or even if you take natural resources, those will be coming from external countries will be looking into that data as well. So there are so the security, of course, because a lot of devices are working, the security must be in high level on all layers. We are not going to talk about the layers that builds IoT, but mainly the perception layer and those two layers include these two, connectivity and the hardware item, So from that point onwards, the security must be built into the cloud, where automation, data analytics will be done and automation will be done, right? When scaling up also, there shouldn't be any security gaps. So these are all the things that are so security in general is a very important thing that is being looked into. So strong security measures including authentication, encryption, access control, and data protection. So those points are mainly general points when coming into data security. Anybody who's doing networking, anybody who's doing cloud computing, in big data, things like that, would be aware of these components, the measures that are being taken to secure that data will be the same. The additional parts would be the individual devices themselves, because the devices themselves will be talking to each other, and that there will be different kind of IoT specified networking being used for different reasons, and in that case special attention must be given to the hardware devices and how they exchange data, what are the protocols they used, is the data they exchange valuable, and if that according to the value, what are the measures that we encryption, or what are the values that we can put. If encryption is there, so to encrypt and decrypt there should be an increase in processing power, so on and so forth, right? Then again, when we talk about IoT system, the main characteristic, so if you take main characteristics, this is a part of the main security, and privacy is a main part of main characteristic of a IoT system. Next feature next to security and privacy is real-time communication. We talked about real-time communication when we were talking about connectivity, right? So part of IoT is real-time data sharing, right? IoT devices often require real-time or near real-time communications for time critical applications. We talked about it in the examples as well. This allowed for rapid response, event driven actions, and timely decision making. So now we can see, okay, we have used IoT to give rapid response, event driven actions, and timely decision making. If we are to look at an example, we talked about this. We talked about the best example is the fire extinguishing scenario, rapid response, quick decision making. We talked about how IoT can be used in such a scenario. Then we can also talked about smart hospital beds and how the monitoring of a patient we can give real-time data to doctors, nurses, so things like that. So the data which is been pushed will be real time on those situations, and the decisions that is needed to be made should be made very quickly, and in thus real time data is needed. Even in a manufacturing plant it would be the same, right? It would be real time communication. If you are remotely going to control another IoT device, that means again it is real time data that is needed to be sent and to be that is meant to be communicated, input and output both. So real time communication, facilitate in real time communication, having enough network bandwidth, the network support, the network infrastructure to facilitate real time communication is a part of IoT, right? Real time communication could come as a subcategory of connectivity, right? When you say seamless integration is needed, if it is real time communication in that scenario, that means we have the network should be able to facilitate that the amount of data which is being created and being passed through in real time. So one of the things that you will now understand is when you have a large scale IoT application, the amount of infrastructure that is needed to have the network running and have processing power and so on and so on is also a lot. So then we started from connectivity. We talked about perception layers, sensing or the actuators inside data analytics, automation and control. We talked about scalability. With all that, we need security and privacy, which is, again, when coming into any technology, it's a key feature or characteristics that is need. Then again, we talked about real-time communication. Real-time communication is a part of connectivity, but in IoT, real-time communication is a must-have characteristic, because if there's a sensor looking at an environment, right, every time, if you see these examples above, right, if you see let's say, okay, if you see an autonomous car driven, it is real-time data. They have to process the data in real time. Whether it is, you have to process the data in real time. So if you take a hospital bed, you have to, or a hospital room where there are IoT components or IoT devices, you have to process data in real time, right? If you have a camera system for security purposes, the monitoring, the surveillance should be done on real time. So there are a lot of instances where we can use real time data, where we can apply a real-time data exchanging application of IoT as a solution, right? It allows rapid response. Again, it's a good example for the fire extinguishing scenario we talked about earlier, right? From that, we go to heterogeneity. Heterogeneity is can be defined as IoT encompasses a wide range of devices, technology, and protocols. IoT systems must handle the heterogeneity of devices, data formats, and communication protocols, ensuring interoperability and seamless integration across diverse platforms. So I'm trying to think of how to tell these examples, but the best thing would be, right, the best thing would be if you look at these examples which are there, right? Some of them are legacy systems, some of them may use different protocols, some of them may have different processing units or things like that, right? Let's start from the beginning. So when we are using, let's say, when we are using a motion sensor can be built by a simple sensor with a simple processor built in one chip, right? In one electronic board, the processor and everything could be there. So there's the requirement of the requirement of newly built components is not necessary, right? You can use commercially available sensors depending on your need, right? So in that case, if you take let's say a Arduino sensor for motions as a motion sensor, so you will be using a set of code which is relevant to that particular sensor. The outputs which are being read is relevant to that. If you take a smoke detector, or if you take like something like a smart fridge, the processing power which is required is far greater. There's a GPU component to it. There is multiple number of sensors involved. So in that particular case, a Raspberry Pi or something higher processing value is needed. Virtual reality gaming is a different kind of a different kind of a beast itself. The amount of processing that is needed is very high. So you can see in each, if all these things are to be connected to the internet and to become Internet of Things, they should be able to talk to each other. This is about compatibility. This is about mainly about compatibility. And if you have to give a outcome in the sense that other actions would take place upon that data which is being received. Let's look at the example of the weather sense of the IoT, right? The weather sense of the IoT would give out a set of data according to that IoT device, right? It will use the protocols that are there in its codes. When coming into networking, it will use its own protocols, right? A different IoT device could be used in a different IoT device which uses a different networking protocol, a different set of sensors, a different it will be a different set of outcomes, right? If one set of IoT devices take their readings out of a analog signal, others might take it from a digital signal. One would be coded in the outcomes would be coded in let's say C++, and the other, let's say, by Python, something like that. So that means in Internet of Things there's a jumble of but to take these decisions, to take this, either to switch on the light or switch off the light, or these any industry or any situation where the real-time data of the weather is needed, right? We need to collect all those different types of IoT devices and put them under one roof, analyze their data, and produce one correct result, right? If you in IoT, that is one of the main points that is needed to be addressed. If you are going to build a IoT system from ground up, it would be much easier than trying to put a new IoT system into a existing IoT system, because the protocols, right? So wide range of devices, technologies, and protocols, right? Basically what is it's trying to say is that the number of devices could be vast, the methods they communicate would be vast, the software which is running, the hardware which is there on those devices would be totally different, right? But IoT system should have the capability to handle the heterogeneity, in a sense, right? In a sense, the differences, they have to be able to handle the differences to either, here it says communication protocols, devices, means the hardware itself, and data formats, right? So interoperability is something that we talked about before. So these different devices with different protocols, different let's say operating systems running on them, either different ways of encryption or whatever, should be able to connect and exchange data between each other seamlessly. This mainly comes like if you are, again, if you have a system which is going from ground up, it's okay. But today in the modern world, there will be legacy systems, there will be different kinds of components which are working in or which are already established, right? If you are a, let's say, again we will go to the weather, right? Because we have example here, right? Now you can see, now let's say you are going to get a startup, you're going to build a startup, and that startup you're going to build an IoT device which can real time monitor the weather, right? It's going to be very easy. Every aspect of the weather will be monitored by a single device, and it is very easy to use that device. You just need to go and fix the device in the place you want to monitor the weather, and that's it. You can then directly connect to it through an app and get the weather from that device. But that itself is not enough. Internet of Things means that device should have the ability, like let's say a government contract comes in and say, okay, we have already 300 devices installed around the country. We want 50 of your devices to be installed to check the weather in positions of the country where we don't have visibility of. And then your IoT device should be able to communicate. That means that IoT device, your startup's IoT device, should be able to communicate with already existing infrastructure, with already existing IoT infrastructure, right? Because those 50 devices combined with the other 300 devices together, the data will be collected and a single real-time situational awareness map of the weather will be created, right? So in that case, when building IoT, we have to see what are the protocols in use, right? What kind of a cloud system that we want to use, and things like that, right? So it is basically right, this property of IoT is, as we told about it, there's a property of IoT which is, or there's a characteristic of IoT is the scalability. If scalability is a characteristic of IoT, that means heterogeneity, or the ability to integrate between different data formats, communication protocols, right? Connecting between legacy devices, old and new, and exchanging data together to give outcome in the IoT world is a must for IoT system, right? Let's say somebody asked that they need to upgrade their fire extinguishing system. They already have a control system, right? And they already have a sprinkler system. They can control the sprinkler system, the water sprinkler system, through the control room. So then there is a connection of IoT. Already the control room can send notifications to the building owner or the people in the building if there's a fire. The only thing that is going to be changed is the smart smoke detector. This will be your product, this will be your application. This would be better than the product which is already there, right? But it doesn't matter if this is good, if the data which has been produced by this is not able to be read by the control system itself. And if the control system cannot read that data, they cannot handle the already existing sprinkler system, they cannot send the notifications, and so on and so forth. So heterogeneity is the ability of this IoT device which is being implanted new to the building, ability to connect with the existing system, ability to connect with the network system which is already there, ability to use the data protocols or data, right, to basically to speak in a way that the control system would understand. That is heterogeneity. So if there is scalability, right, heterogeneity would be a part of it. Interoperability will be a part of it, right? Then edge computing, another characteristic that we would see. IoT devices generate vast amount of data, and processing all of it in the cloud may introduce latency and bandwidth constraints. We talked about this. So we talked because we see that the amount of resources that is needed to process this data is also a little bit high, because if there are vast numbers of IoT devices, that means a vast number of data is created. Edge computing brings computational power and data processing closer to the device, enabling faster response time, reducing bandwidth usage and offline capabilities. Okay, so what does that mean? What does that mean? What does it give? Is it an important characteristic of IoT or not? Edge computing. What this means is that not all the data which is being collected by a sensor needed to be sent to the cloud to be processed. Only the data which is needed. This is mainly for resource handling. So let's look at edge computing, right? So edge of the node would be a IoT device. Let's see how it works, how it helps. Let's take the Roomba vacuum in a smart home, right? There is a proximity sensor. We know it. We have discussed about it. There are a set of actuators which work to move the vacuum up in a straight line or change its direction. There are again vacuum and those actuators working to function this Roomba vacuum. But if you look at the bigger picture, do we need this proximity sensor data going into cloud processing unit in real time and sending the data back again to the actuators and telling it to turn? Is that a necessary step to be taken, or we can simply introduce a small processing unit for this Roomba where the data collected by the motion proximity sensor can be processed and the actuators can be ordered in a way to change the direction? That can be done. We do not need computational power of the cloud itself, right, to take those decisions. So in edge, so what we do is we cut off that particular point, right? We we don't need to share that data, we don't need to use bandwidth, we don't need to use cloud processing power to do that. We end of the day, when the whole area is covered and when every part of the flow is cleaned, the vacuum can send a notification that the job is done to the smartphone through the internet. No need to tell that I'm going to crash into this place, so I'm changing directions, what are the things I should do. Those things are not needed. Those can be automated inside the room by itself. So that is an example of edge computing. At the very end of each, if you take IoT as a cluster of network devices, in each node of those clusters has a device with edge computing, right? And for example, the smart lock, if only like the data set that is being kept inside the smart lock is more than enough to keep fingerprint stored, and if needed to compare the new fingerprint with the archive it has, it should have the processing ability for that particular data of the fingerprints archive set, and the processing power of comparing the new fingerprint and the and the archive set fingerprints, that shouldn't, we can isolate it to the lock itself. It doesn't need to send those data, save those data in a cloud system, and spend time sending the pictures of the images of the new fingerprint sensor to the cloud, then checking with the archive and so on and so forth. All the processes can be done here, and if programmed, only a notification will be sent into the internet, and through the internet to the smartphone of the owner, telling that, oh, this person have entered this building or this room. So edge computing is when we use the processing ability of the IoT device itself to process data which is coming from the sensors, right? The computing aspect of it, rather than going to the cloud, right? Rather than carrying out the data analytics and those large number of data in a cloud system, we process it inside the device itself, right? So it will provide it will save bandwidth, right? And it consumption of power and data processing closer to the device, yes. Enables faster response time, yes. Think about again, we can think about the Roomba, or we can think about actually autonomous driving vehicles. If the self-driving vehicle itself is a IoT device, right? What will happen if the Tesla vehicle have to communicate through a satellite into a cloud and input all the proximity data it collected and wait till a response comes in to push the brakes? Definitely it will crash, because there's a latency which will definitely happen. When the amount of number of cars increase, the amount of the queue for processing will increase, so there will be not enough resources. Definitely then the cars would be crashing into themselves at all times. So that particular part is stopped by edge computing. The processing power to make decisions to drive by itself is inside the device itself. When only when they need to share the data of their route or the location or things like that, emergency services or things like that, only then it will communicate with the cloud. So in edge computing, here this is a good example of edge computing, that processing power and everything is given to the car itself, so to stop again bandwidth issues and latency issues, because it is very time sensitive when coming into driving a car autonomously and driving it without crashing into something, right? It will give offline capabilities as well, right? And now edge computing itself is a part of IoT. If you have studied embedded IoT devices, you may have worked on edge computing device. If you have built a IoT device by yourself, it could be a simple fingerprint reader. It could be a proximity sensor, a small IoT projects. You will see most of the IoT projects you see on the internet, on YouTube, and so on and so forth, are good examples of edge computing. They don't use the cloud to make the IoT device work. The processing power itself is on edge computing. So to summarize, if we are to apply IoT, for different industries or domains, right, to solve specific challenges, improve processes, enhance decision making, and create value. If we are to apply IoT to industries and domains to solve specific challenges, improve processes, enhance decision making, and create value, we would see these characteristics: connectivity, sensing and perception, data analytics, automation and control, scalability, security and privacy, real-time communication, heterogeneity, edge computing in that applied IoT system. We will see these characteristics, right? Characteristics 1 and 2 definitely will be there, right, alongside with rest of the characteristics, right, depending on the situation. For example, real-time communication is needed for weather monitoring devices, but real-time communication would not be needed for a smart fridge, right? So things like that. Now we know, okay, what is applied IoT, right? Then we looked at, when applying IoT, what are the characteristics that we will see in the IoT system. So now let's take an introduction to machine, right? Now before going into anything else, let's talk about let's look at, before looking into anything, let's see the direction that we are going to, or the direction that we are looking at on this applied IoT lectures, right, on this applied IoT course, right? We started by talking about IoT devices, right? We started from simple IoT devices. The examples were mainly about domestically used IoT devices. Then we came into a little bit of industrially used and a little bit of large scale applications to it, right? Then after that we talked about applied IoT, and in the applied IoT sector, domestic use of IoT or small devices of IoT becomes a small topic, and we started talking about different types of industries and different types of domains, right? Which is nothing of which is small scale. We are talking about large scale IoT applications when we are talking about applied IoT, right? If you are measuring a power grid from top to bottom, right, it's something that expands throughout a country. It won't be small. If you're talking about agriculture, vast amount of lands, vast amount of crops, different types of crops. There's water management, there's pesticides and those crop management side. Then there is fertilizer management and how IoT can work on those things as well. Logistic goes nationally, internationally as well, when coming into ships. So we are talking about um, vast industries which use IoT as a solution for their problem. And we talked about why we use IoT, why we apply IoT to solve specific challenges, improve processing, enhance decision making, and creating value. So those are the main reasons. Everything comes under that category. Then we talked about characteristics of IoT, and in this you would see that we have moved away from embedded IoT systems, domestic IoT, small devices, or couple of devices working together, or even 10 devices working together. We have moved away from that, right? From these characteristics itself, you will see that we are now talking about large scale application of thousands and thousands, even millions of IoT devices working together. That is why the data analytics comes in. That is why the automation control, scalability, security, and rest of it comes in, right? And because of, we also highlighted edge computing and heterogeneity for mainly for balancing out the large amount of data which is being created, to balancing out the processing of it. Heterogeneity to show that these IoT networks would be so vast and so many devices will be there, that the compatibility will also be a characteristic of it. So little by little we are moving from general small applications to vast scale uh, high industrial applications. So before going into more towards how IoT is used in different domains or industries, we should take an introduction to a terminology which is called machine to machine, right? M2M. So introduction to machine to machine. Machine to machine, or M2M, refers to the direct communication between two or more devices, typically without human intervention. It involves the exchange of data, commands, and information between machines, enabling them to collaborate, interact, and perform tasks autonomously. So if we look at that definition, right, let me go through that definition again. Machine to machine, or M2M, refers to direct communication between two or more devices, typically without human intervention. It involves the exchange of data, commands, or information between machines, enabling them to collaborate, interact, and perform tasks autonomous, uh, autonomously. This definition is quite close to a definition of a IoT device, or definition of IoT devices working together in an automated system where there is no human interaction. When we talk about examples, some in IoT, some examples there's human interaction in the control center or when receiving notifications and things like that. And there are automated systems, autonomous systems, such as right, such as the water sprinkler system, where it would the smart smoke detectors would detect the smoke or the fire. The control system will process the data and activate the sprinkler system of that particular location. So from that example, or from this one, it will IoT devices will check the light intensity of sunlight. That data will be passed through the internet and will be checked whether the light should be switched on or off depending on the intensity and the parameters given. Thus the autonomously the lights will turn on. No human intervention is needed. Same thing goes when we are talking about temperature control again. So now we can see devices or machines working together, right? So this M2M concept was there in mainly in industries. In the industrial is a term that is used in industrial circles or in the domain of heavy industry and those things, right? before IoT before IoT, legacy systems or old systems, before all these sensors and things that came around, legacy systems had huge machines with legacy programming which are working with each other. It is very similar to IoT today, right? Machine to machine communications is today's today without IoT, machine to machine communication is not possible. So another way of looking at this machine to machine communication, though it goes it comes before IoT. It was machine to machine, M2M was born before IoT. It with today's technology and today's world, IoT has basically become M2M, or M2M is now a subcategory of IoT with the technology we have today. But the main thing that should be taken out of this is machines exchanging data, then exchanging commands, meaning that data is processed and commands are given out, or information between machines, right? Exchanging information between machines, enabling them to collaborate, interact, and perform tasks autonomously, which means they are functioning without human interaction, right? They're functioning without human interaction by speaking between themselves, right? Have we seen this in before examples? Yes, we have. Autonomous driving vehicles have an array of sensors which collects in data and talks to the brakes, to the motors, to the any other actuator which is in the car, steers the vehicle and drive the car by itself, and all those small sensors would be talking to each other, and those devices, those internal devices of the vehicle would be talking to each other, exchanging data, and doing things without human interaction. Autonomous means the machine is working by itself without any human input. And this is what is being expected in M2M or machine to machine functions, right? Machine to machine refers to the direct communication between two or more devices, typically without human intervention. That is the normal sense of things. There can be some kind of human intervention, there can be some kind of human monitoring, but mostly the functions are done by themselves. It involves exchange of data, commands, and information between machines. These things we talked about when coming into IoT, enabling them to collaborate, interact, and perform tasks autonomously. So if they are to work autonomously, that means working without human intervention, right? So are there examples for these things? Yes. We will look at the examples, right? But now we are moving to a part of where entire automation processes are taking place where human intervention is not needed, right? This is being enhanced and achieved by IoT, right? If systems to work autonomously, right? If systems to work autonomously, they have to have the capability of gathering data, right, before carrying out its commands or function, to see if the parameters are met or not, right? Those things are done either through IoT devices and so on and so forth, right? So industrial automation is the biggest topic that is there for machine to machine. M2M enables the automation and optimization of industrial processes such as manufacturing, supply chain management, and logistics. Machine and sensors communicate with each other to monitor and control operations, improving efficiency and reducing human error. So in industrial automation, machine to machine is implemented. Machine to machine enables the automation and optimization of industrial processes such as manufacturing, supply chain management, and logistics. Machines and sensors communicate with each other to monitor and control operations, improving efficiency and reducing human error. So when we are defining this, we can see that machines and sensors, when machines are fixed or collaborated with sensors, automatically it will become a IoT device, isn't it? From the definitions that we have seen before, right? If you take best example, again we can go to the autonomous cars. If it was just a car, or if you take cars from 1980s or 1970s or the good old days, everything is manually driven, no sensors involved, right? Everything is manually driven, no sensors were involved, and everything could be fixed without using a computer or scanner. That means it's a machine, and when that machine is fixed with if with a proximity sensor, accelerometer, gyroscopes, cameras, processing power, networking, so motors to handle the pedals and move the steering wheel by itself, then you have a autonomous driving vehicle. So here in machine to machine, we are seeing that in industrial automation, machines and sensors communicate with each other to monitor and control operations. So we are quite seeing the same scenario, right? So we talked about we will veer off topic for a small moment here. So when we talked about machine to machine, I told that machine to machine is a term that came before IoT devices. This is there because of, if you take something like a printing press or something like a bottling plant, or even if you take water purification systems or pumping stations or places like that, the machine itself, like if you take a paper printing center, right, some time ago, that machine itself there are several machines working together inside to print that paper, right? There's a whole manufacturing line, and that full line is automated. Each machine is talking to itself. If you take steel manufacturing also, it's a steel manufacturing line which would have couple of machines working together, right? They are not advanced systems. They don't have very sensitive sensors or things to monitor, things like that. They are purely, most of the time, mechanical devices, but they work with small electronic parts, but they somehow find a way to communicate not a large amount of data, but sufficient amount of the data between each other to carry out a function, maybe construction or manufacturing, somehow together, right? So when talking about machine to machine, it is that machine to machine is something as a concept is before IoT. That is something we talked about, and today or moving forward, and you will see through the examples themselves, today the difference between IoT and machine to machine, the lines are blurred. There's no clear definition between those two, but in future slides we will talk about machine to machine and Internet of Things. We will see the differences between each other and try to understand what are the differences, and try to understand what are the requirements to have machine to machine or IoT system. But basically, generally, with the technology today, the lines are blurred, right? But again, I told you that M2M is a concept that comes before IoT, right? So very, very long time ago, I mean, before basically mainly you guys are born, I think it's safe to say that. So we are talking about 80s, for example, right? ATM machines were there. IoT as a concept was not there. Point of sale machines, barcodes and things like that. Those were there. Those machines were talking to each other, right? Accepting a card with data in it and processing that data and communicating it between. So those are machine to machine systems before IoT as a concept. Vending machines also comes into mind. The other one is legacy security systems. Though image processing and looking at the image through internet or remotely surveilling a place in real time comes under IoT, there are still legacy systems which do basic things such as record video and just keep an eye on a particular area through a camera. So those things were there. Then again, in the industries of oil and gas industries, these are heavy industries, heavy machinery is being used, and before computerizing or before there were control systems, before IoT devices were used to operate these machines, right? Either IoT devices would be used as add-ons to the legacy machines. These legacy machines had the capability of functioning by themselves or communicating to each other, right? This task is completed by me, now next task you have to the next machine have to do. A printing press I talked about. Then steel manufacturing, same thing. The steel manufacturing processes, most of the controls are done either remotely through human intervention, or the press itself is automated to press the steel properly, cut the steel automatically, handle the hot molten steel automatically. So these processes were there before even IoT as a concept. Mining operations, same scenario. Even here you can see today that a control station would look like this, and the remotely driven vehicle is doing the digging, so the humans are safe. So this device would be a machine and it would talk to maybe other machines that are there inside, because could be two separate parts, one for digging, one for the movement, right? So the engine would be talking to the lifting equipment and increasing the power, reducing the power. So these things happen. These things are there before IoT came into play. GPS was there before IoT coming into play. So logistic wise, keeping eye on the logistics and things like that, where they are at which time, was generally done by whomever has the ability to access GPS. And there were GPS tools used. Even today it is used, even as IoT device. Now it's used to monitor the logistics or where the vehicles are, right? So again, today the use of IoT have supported machine to machine communication, and when coming into industrial scale application, the line between machine to machine and IoT is blurred, right? Like it is most probably one, rather than talking about two different topics, right? When we start talking about machine to machine, right, from the definition itself we could see that this looks similar to IoT. So again, M2M as a concept in the 21st century is similar to IoT, right? Because the main differences would be the amount of sensors that is being used in automation. In the 80s, machine to machine would be there, right? If you take this pumping station, machine to machine would be there, in a sense that uh, it will only either work in timing, or it would work depending on the pressure going up and down. But if you have a IoT system installed, it will check the pressure of each tube, each location, the temperature, the amount of electricity consumed to pump those data. So it's a vast amount of vast set of data when using IoT, right? It is very easy to automate these systems using IoT because the amount of data is so vast that accurate decisions can be made, right? I am a little bit like uh, struggling to explain to you the difference between machine to machine and IoT, because basically if you try to search into these topics and if you try to see what is what, right, by definition you will see that, oh, this is IoT, right? And even in when coming into IoT, we cannot just say a single sensor is IoT. A multiple set of sensors, an embedded system would be IoT, right? Here, in machine to machine communication, we could see that robotic arms working together to build, right? In this example, let's go through the examples and we will try to understand machine to machine. And while going through these examples, you will definitely see that today Internet of Things have taken over machine to machine. So if you take these robotic arms working together, right, in a machine to machine environment to build vehicles, they are pre-programmed. They would know what is to be done and in which number of steps and where to move in which step. These things are pre-programmed, right? And these arms are in constant contact between each other. When one arm finishes the initial step, the next step would be followed by the next arm, then the next step and the next step. We have seen in vehicle manufacturing, humans are mostly there today just to monitor these systems with if they are working without any error or malfunction. Most of the at least 80 to good 90% of the work is completed by robotic arms. So we talked about these we talked about, when talking about robotic arms as an example of IoT, we talked about the number of sensors, actuators, right, cameras, proximity and gyroscopes, to pumps, motors to turn and lift and close and so on and so forth. We talked about those actuators. If you have studied IoT, about IoT and not applied IoT but IoT itself, you will see that as an IoT device, this is a very good example. And IoT devices talk to each other through network. Machine to machine is also the same. There will be, of course, a processing power either built into it through edge computing, or there will be processing power definitely inside the factory in a cloud, in a data center, right? So that each arm is networked to the data center, and the data center will be collecting all the data and processing it and telling the machine what is needed to be done, or orchestrating the machines step by step the work needed to be done. So basically, one machine finishes its work, the machine talks to the other through the network or the data center to do the next work. It is not necessary to be connected to the internet itself to carry out this work. If the code is there, if the processing ability is there on the factory floor itself, intranet which runs through the factory floor itself is more than enough to carry out those functions. So when will it become IoT? Basically, we talked about IoTs and we talked about edge computing before as a characteristic. So we can see that this factory itself would be a part of edge computing if there's a data center processing all this data. So let's say let's say BMW, the manufacturing plant is at one place, the headquarters are in another place, and if the people in the headquarter office needs to see how these machines are functioning, are they functioning at their optimal levels, what are the health level of these machines, are they overheating, are they broken down, are there problems in the manufacturing line or things like that, the quality of the vehicles, so forth and so on, or if there are mistakes happening while manufacturing these things. So monitoring these things can be done remotely, and that means at that particular point that data needs to be sent through the internet to the headquarters. So in that particular point, that factory and everything in it becomes a thing of the internet. But without that, the as an IoT device or as a machine to machine concept, the factory could process the data itself. So industrial automation, that means putting everything into all the commands into a code and making machines do it by themselves, right? Or basic way of saying industrial automation is taking the human touch out of it, taking the human out of the process and letting machines carry out the process by itself. So again, good example would be the manufacturing of vehicles, because this is one of the commonly seen examples and one of the best to show to. Then we have a pumping station. Again, this pumping station could be to pump water into a city, or to pump water into a nuclear power plant, or pump water, or even pumping oil through a vast pipeline. It could be anything in between. It is an industrial application. So the there will be a constant amount of pressure that is needed to be maintained inside the pipes. If that is the case, each motor should speak to the other motor, right, and tell, okay, motor one over here is giving their maximum capacity, right, pumping at their maximum capacity, but the pressure inside the pipe is not enough. Motor 2 needs to activate, then it will rev up and see how much it can come. Still it will not be enough, then motor 3 will be automatically switching on, but then it will find out the pressure levels are now coming to normal, so only half the capacity is needed from pump number 3. Only pump number 1 and pump number 2 needs to work in their maximum capacity. Or it could be distributed, the pumping will be distributed among 3 or 4, 75% each, things like that, right? So the machines, so no human intervention is needed. The pressure, you can see the pressure gauges, the pressure is being measured. Through that, having a small circuit is more than enough to control these motors, which are, again, rather than being IoT machines, they are legacy machines, and they can talk to each other and work. So machine to machine is talking to each other and working. Again, if we need to make this IoT, we can have pressure sensors. Not only here, we can have pressure sensors throughout the entire line, and that could be connected to a network, and it will properly monitor if there are any leaks or if there are any problems. This is a good example. Think about, so these machines can talk to each other to measure the pressure inside the pipes. They can maintain the pressure. If there is a loss of pressure, they can monitor it near the mouths, and they can increase the pumping capacity. But if the pressure reduction is happening due to a leak somewhere in the pipeline, that have to be monitored through something else. Here in that case, IoT comes into use, because vast number of sensors throughout the pipeline. Maybe the pipeline will go for, let's say if it's a oil pipeline or a gas pipeline, it will go for couple of hundred, even 1,000 kilometers, even more than that. So that whole line needs to be monitored. That is, so that data itself can be even remotely accessed by people by engineers who needs to attend that place, and so on and so forth, when it is shared through the internet with relevant parties. Otherwise, this will be a machine to machine interaction. One machine would be checking the pressure, and then the command will be there to the motor to carry out the next function. So in an industrial application, pumps are being used for various number of reasons, and this is a good example of machine to machine interaction. Then again, logistics, machine to machine interaction with a bit of IoT, right? We have automated this is Amazon's, I think this is Amazon's automated distribution centers, right, using these autonomous driving or autonomous vehicles to send the packages to the correct location in this distribution center. And of course, we know that these are fully autonomous, and they are the machines definitely talk to each other to move around the floor. And of course, then again, this is a machine to machine interaction, but we can again quantify these machines as IoT. So when we are talking machine to machine today, you can see why I am telling that there is a blurred line between machine to machine, because everything today, every machine can be a IoT when it needs to, right? So here we have a remotely operated mining system, right? Controls are with a human, of course, and there are pictures and a set of data that has been represented to show the location also, or to show the surroundings of the machine, right? So in this manner, the humans are safe, right? If it is a IoT device, there will be tons of sensors giving tons of information back, showing the driver that how's the tire pressure, how's the situation inside the mine, is the engine or the motors are working properly, if the lights are working properly, the video feed, the amount of cargo that it is carrying, so on and so forth, right? Then right, so then again, that this is an example where human interaction is there, and we have the joysticks and everything, and this machine is talking to a machine inside the mine through network, right? Everything would work through a network, right? This is used as an example for human interaction where machine to machine is working. These are examples of machine to machine itself, right, working by itself. But end of the day, right, end of the day, this all seems like part of IoT, isn't it? That is why but in the syllabus the concept of machine to machine was there, right? But again, though it is machine to machine, we can give IoT solutions for machine to machine situations, right? I think the expectation would be, if you take these pumps, right? These pumps are machines, but they are not IoT devices. These machines can be operated through data which is collected by IoT devices, would be pressure sensors. But when they suddenly turned into the IoT system itself, right? When IoT sensor is, so these machines would be then actuators. So the difference between machine to machine and IoT, the lines are being blurred. But machine to machine as a concept was there before IoT, before the time when large amount of data could be sent through networks, before the time where large data centers with shared resources have the give capability of the cloud. So M2M is today, with all this virtual reality and with IoT and AI taking center stage, machine to machine is becoming a legacy concept. But another way to look at it is, machine to machine is a section or a subsection or a part of IoT. Okay, so industrial automation, it is very clear. We talked about many examples, and many examples should come to your mind as well while talking about industrial automation. From industrial automation, we will go to smart grids, right? M2M communication plays a crucial role with modern power grids by allowing intelligent monitoring and management of electricity generation, distribution, and consumption. It enables real-time data exchange between smart meters, power plants, substations, and control centers, optimizing energy and usage and improving reliability. If you have smart meters which is connected to the internet, and the grid operators have the ability to understand how much electricity is consumed by a smart city or a location or something like that, it becomes part of Internet of Things, isn't it? But then again, these are working, we can say, we have programmed everything, just these machines to talk to each other and work. But of course, again, M2M as a concept was born before smart meters were there, okay, before solar panels were there, before wind power plants were there. So we have to look at M2M and a IoT mixture. When we are talking about M2M and when we are talking about IoT, right, we can't differentiate them between each other in today's concept. If somebody asks, I need a M2M solution, you're basically looking at IoT solution, right? So you cannot separate this. That is why this becomes M2M, communication between machine to machine by itself becomes a very important point in applied IoT. Now we are going to industrial scale examples, right? But before going to anything else, right, we have already reached 2 hours, right, in this lesson, right? So I would continue. I would continue the lesson going forward. But okay, let's talk about smart grids, and we will stop from here, and then we will continue for the rest of the topics next time, right? So yes, we are talking about smart grids, right, and how M2M works, right? So we have the power generation, transmission and distribution, power storage and consumers. So in this side, power generation side, we have thermal power plants, which could be coal or gas powered. Even petroleum is used to power plants. Nuclear power is another point. Wind, solar, hydro are environmentally friendly, comes into environmentally friendly categories. But then again, let's talk. So when you talk about solar power plants, if you are talking about and wind power plants, that means if you are talking about IoT devices, we will get weather information from IoT devices to optimize these methods of power generation, right? Mainly wind data from past data from weather monitoring devices on the wind. Solar panels, of course, can be automated to be fixated on the location of the sun throughout the day, thus increasing the efficiency of the solar panel, right? Hydropower plants, nuclear power plants and thermal power plants can be controlled by the amount of electricity which has been consumed, which can be again estimated through IoT devices, right? If we want to, we can inside these machines, if you take thermal power plants or nuclear power plants, which nuclear power plants themselves are very complicated machinery and very sensitive machinery. There are many safety protocols that is needed to be followed, right? There are layers and layers of safety systems built to it. If one fails, the other to take over. So these things are there. So every machine can talk to the other machine to see if the cooling plant is working correctly, the amount of reaction taking place, things like that, the amount of heat generated, the steam pressure, so on and so forth. Same for thermal as well, the steam pressure, the amount of heat generated in the machine, so on and so forth, right? So the machines itself could be talking to each other, and maybe emergency protocols will be programmed. In nuclear power plants, the fuel rods can be pulled out, or the plant can automatically shut down if something goes wrong. So those can be adjusted when machines are talking to each other. The reactor can give readings of radiation, the amount of heat generated, the pressure inside, things like that. And depending on that reading, the power plant can, if the reading goes out, it can automatically shut down. So transmission lines, Again, we talked about how transmission lines can be monitored. uh, lines can be have to be monitored, and they have to be maintained. They go for hundreds of kilometers, and we can use IoT devices or other machines to monitor these things, and those information can be communicated to a control center, right? The amount of electricity that is being consumed, either energy storage, industrial plants, smart cities, can smart homes, can those things can actually give readings of how much energy is consumed, and that data will be fed into a control center. The control center then can adjust the amount of electricity being produced to match the needs of that particular area. Extra energy which is created can be stored in energy storage devices. We can then keep the energy storage device can talk to the power grid and say, I have this much capacity left. If there is any extra, you can route any extra electricity towards my side, I will store it. And if the grid is losing electricity, then the grid can talk to the energy storage device and take energy out of there. Talk to means they are not going to knock on the door and just take, but that means automation and code will be running to and constantly real-time reading of the electricity grid, the amount of electricity being used, and basically the amount of supply will be always monitored. And when the supply goes down from demand, energy storage just can be activated, and energy can be pulled out from that end. So things like that, machines talking to machines, right? When there's wind, the wind farms will get activated, and maybe a thermal coal power plant can be shut down, good for the environment, and things like that. And sometimes when it's at the peak, wind power will start to work. Then there will be extra energy that can be stored, and when there's no wind, then the energy storage can produce electricity, so on and so forth. So the elements that are there that is needed to be talked to each other is a lot, and those elements, especially the machines inside power plants themselves, talk to each other to become efficient and work without human intervention, right? The machine right, like if you have a thermal power plant, right, which produces heat, that thermal power plant would need to monitor the amount of heat it produces, the amount of energy, the amount of material it consumes. If it is a gas power plant, or if it is a coal power plant, or if it is a petrol or gasoline power plant, it should have the ability to monitor the amount of material which is there to burn in its storage, right? And it should be able to read the amount which is being expected to be produced by the control center. It should be able to understand how much pressure could it generate before causing harm, how much water to boil, how much steam that can be produced without an explosion to run the turbines. Is the turbines working at its maximum capacity, at maximum efficiency, or does any of those machines need any uh, refurbishment or needed to be looked after, done checks and done any services to it, things like that. Topics are endless, right? Machines talking to machines when coming into producing electricity grids. But then again, machines talking to machines in smart electricity grids is today a part of IoT, and it is a part of M2M as well, right? There will be plenty of if you take a smart grids, the amount of elements that is in play, right? Transmission lines, monitoring transmission lines itself, monitoring the electricity flow through these transmission lines, the health of the transmission lines, the amount of energy consumed by homes, by the city itself, industries. If you put, if right, this is a smart grid, right? This is machines talking to machines inside the grid, and if you add this to Internet of Things, right, when if this is added to the Internet of Things itself, you can get the information of, we talked about this earlier, we can take the information from the weather and see how cold it is, is it going to be cold. If that is the case, more electricity is going to be used for heating up houses and buildings. That means we need to produce more electricity, or either we need to take electricity from the storage, right? So on and so forth. The elements, the amount of elements and things that are there today is far too many. And automation, we have come to a level where in automation where machine to machine communication and automation is now blurred and absorbed into the IoT sphere, right? For now we will stop there. We will stop at the smart grid, right? We can then talk about transportation, fleet management, and healthcare. Then again, it's going to be the same as using IoT, right? So machine to machine and IoT are, it's the two sides of a same coin, right? We will talk about smart cities. In smart cities, we will move to massive number of topics which we can use machine to machine or IoT to answer those problems in smart cities. Then we will talk about these rest of it to understand the difference between machine to machine and IoT, or the subtle differences between them. Additionally, we will a little bit talk about, we will step off the topic, we will step off the syllabus topics and learn about operational technology as well, because operational technology is a word like M2M, OT is like a word like M2M, where IoT is being used. So for today we will stop it from this point, and I will see you in lecture number 4, where we will start from transportation and fleet management in M2M. Thank you, everyone.